Wanted to work through a problem that involves relativity and specifically involves time dilation, one of the important features of relativity. In this particular problem, we're thinking about a subatomic particle, a unstable subatomic particle. It's a subatomic particle that has a short lifetime. So this particle is called the pion, and the pion has a lifetime that's 26 nanoseconds. So that's 26 times 10 to the minus 9 seconds, a very, very short lifetime. When we say the pion has a lifetime of 26 nanoseconds, we're meaning the pion has a proper lifetime of 26 nanoseconds in its reference frame. In its own reference frame, where it is stationary, its lifetime is 26 nanoseconds. If we were to observe it in a different reference frame where it is moving, then we would observe a different lifetime. We would observe a time-dilated lifetime. And that's what this question is about. So we're told that the pion is traveling at a speed that's close to the speed of light. It's 98% of the speed of light. And we're asked to calculate the observed lifetime when it's traveling at 98% of the speed of light. And we're asked to calculate also the distance it travels during that lifetime. And then finally, we're asked to figure out the distance it would travel during its lifetime if there wasn't time dilation effects. So those three questions. There's a little sketch over here on the left-hand side to go with the problem. Here in red is the pion with its proper lifetime of 26 nanoseconds. Here's an observer watching the pion as it travels by, and this observer sees a moving pion, kind of equivalent to a moving clock. The tick of this clock is the lifetime of the pion. And so the observer sees a time-dilated tick of the clock, a time-dilated lifetime, because the pion is moving. So let's go ahead and answer the various questions. I'm just going to begin by writing down the quantities that we're told, the quantities that we know in this problem. So T naught, that's the proper lifetime of the pion. That's 26 nanoseconds. V, that's the speed the pion travels at in the observer's frame of reference. That's 0.8 of the speed of light. We can calculate that from that, the Lorentz factor that's important in time dilation. We give it the symbol gamma. It's 1 over the square root of 1 minus V over C squared. Since we know V is 0.98 times the speed of light, and we're dividing here by the speed of light, this factor in parentheses is 0.98. We've got to square it. We've got to take the difference between 1 and that value, and then take the inverse of the square root. And it did that ahead of time. I got 5.02 for the Lorentz factor. And finally, I'm also going to write down the speed of light. And I'm going to write it down. Normally, I would write down 3 times 10 to the 8 meters per second. But what's more relevant here for this very short-lived pion is I'm going to write it in slightly different units. Its speed is 0.3 meters per nanosecond. So that's equivalent to 3 times 10 to the 8 meters per second, but it's just a more convenient unit here. Okay, first question. What is the lifetime of the pion as observed by the observer, who's seeing a moving pion at 98% of the speed of light. So this is going to be a time-dilated lifetime. The pion's going to live longer. Its clock ticks slower. That 26 nanoseconds gets stretched out. And the equation for this time dilation is that the time dilated time is equal to the proper time times the Lorentz factor gamma. And we know both gamma and the proper time. Gamma is 5.02. The proper time, the proper lifetime was 26 nanoseconds. If I multiply one by the other, I already worked it out, 130.7 nanoseconds, about 5 times longer than the proper lifetime. Part B. Part B says, how far does the observer see this moving pion travel during that time? Well, to calculate that distance, I'll just call it L. We can just use the relationship between distance traveled, time taken, and speed of the moving particle. So the distance traveled by a moving particle is the speed of that particle times the length of time that it's traveling for. We know the speed of the particle. It's 98% of the speed of light. We know the time is traveling for, as seen by the observer. That's 131 nanoseconds. And so I've just got to multiply those two numbers to find out the distance the observer sees the time-dilated pion travel for. And so to do that, I'm going to take 0.98, that's the 98% of the speed of light, times the speed of light. I'm not going to write it as 3 times 10 to the 8 meters per second. I'm going to write it as 0.3 meters per nanosecond. And then I'm just going to multiply this quantity here by the 130.7 nanoseconds. You see here that the nanoseconds in the numerator and the denominator cancel each other out, just left with the units of meters. So that's the convenience of working in these units for the speed of light. And if I multiply 0.98 times 0.3 times 130.7, I got 38.4 meters. So that's the distance traveled by the pion as a result of the time dilation of its lifetime. What about if time dilation didn't exist? If time dilation didn't exist, then the distance traveled, I'll call it L prime, by the moving pion, again by the relationship between distance, elapsed time, and speed, would be the speed of the pion times its lifetime. But now this lifetime is the original proper lifetime because there's no time dilation effect. And so to calculate this new distance that is traveled by the pion in the absence of time dilation effects, I've just, again, got to multiply the speed. It's traveling at 98% of the speed of light, and the speed of light is 0.3 meters per nanosecond. And I got to multiply that by the original proper lifetime, because there's no time dilation now, 26 nanoseconds. And if I carry out that calculation, I get 7.6 meters. And so this is an example problem involving relativity. It's an example problem involving one of the special features of relativity, and that is time dilation. That different observers in different frames of reference see different intervals between events. The event here would be, say, the birth of the pion, the creation of the pion, and A second event would be the disappearance, the decay of the pion. And so different observers, for example, somebody in the pion's frame of reference or somebody in the Earth's frame of reference, would measure different times, elapsed times between the creation and the destruction of the pion.